Hey guys, I was just talking to a couple of your classmates and realized that perhaps a screencast where I explain intermolecular forces and how it is possible to have a molecule with more than one force is actually possible. So that's what this video is for. Okay, so let me talk first about, let's just kind of back off a second and talk about the different types of intermolecular forces. All right, if I have a molecule, let's say helium. I have a nucleus in here and I've got two electrons. And I'm going to define a space around that nucleus where those electrons are actually moving. And they're really moving randomly around in that volume of space. And I really don't ever know where they're going to end up. I know that there are like positions that are defined by calculus where they might end up, but they are randomly moving around in that electron cloud. And it is possible that at any given time, those two electrons may end up next to each other. All right. Now, what happens when that occurs is that I have now created this region of electron density that is shifted to that side. So I have this sort of negative side. And sort of by default now, since there's like no electrons on the other side, now the other side of this is positive. And we can see this distortion of the electron cloud. It looks sort of like this. So sort of here's the nucleus, here are those electrons, and this is negative, and so this side is positive. All right. Now, what's going to happen if that helium atom is near other helium atoms is that for this guy's electrons that are moving randomly about within the its own electron cloud now are going to be attracted to this positive nucleus. So its electrons are now going to sort of migrate to that side also and create a region of negative charge over here and a positive charge over here. Now, this attractive force between multiple atoms, in this case of helium, that is the London dispersion force. Okay. Now, the thing that is tricky about the London dispersion force is that because these electrons are always moving around, as soon as that force is created, it goes away, right? It is temporary. It's literally for an instant in time. And so when we think about the London force and what can increase sort of how strong a London force is really a matter of how frequently those London forces occur in a substance. So let's say I'm looking at helium, right, with two electrons versus like xenon with like 54 electrons. Now, it doesn't mean, so this is helium and this is xenon. It doesn't mean that I need all 54 of those electrons on one side. I need more than one. So the likelihood that two of xenons will end up on one side is much higher than the likelihood that all two of heliums are going to end up on the same side. So the frequency at which an atom of xenon would have attractive forces with another atom of xenon is higher. So I increase the number of electrons, I increase the frequency of LDFs. Oops, LDFs. Okay. So hopefully that part makes sense. Now, this increases with molecular weight. So the more either atoms I add or the more electrons within those atoms, I'm going to increase the frequency and the magnitude of those forces as a whole, the summative force. The other thing to consider is the shape of that molecule. So let's say I have, in the example he used was if I have some carbon molecules and I have carbons sort of that look like this, they're like tetrahedral, and I'm not representing here the hydrogens, but let's say I have a long 1, 2, 3, 4, 5, 6, 7. That is whatever is the prefix for 7, I forget. But let's say I have two of those molecules that are like in space, and each one of these, there's hydrogens on here, hydrogens up here, right, like that, and this one too. So all of these atoms can engage in London dispersion forces. And they can have like little points of contact all down the length of this chain. And all down the length of this chain, they're having these LDF forces. Now let's say I have the same, I have C7H whatever, but instead of the way those are attached all like in tetrahedral, let's say it's more branched, so I end up with something like this, you know? And so this looks sort of like a long skinny thing, and this looks more like a circle. So now I have like all these places all down here that I can have LDFs, but if I have two of these guys, now there's only like two, you know? So the number of times that these guys are going to engage in London dispersion forces and hold themselves together is actually far fewer than a long skinny one. So this guy would have stronger London dispersion forces than something like this, even though they have the same number of atoms and the same types of atoms. All right, so that's London dispersion forces, and everything can have those because everything has electrons that can move and have a cloud that is polarized, what we call polarizable, where you can actually change the electron distribution in the electron cloud. All right, now let's say that I have a substance that's got like H3C, C, O, like this, CH3. Now, remember, I can have these guys engage in London dispersion forces with each other. That's a single bond, my bad. So these guys can have LDFs because their electrons are moving around. That's totally cool. But I also have now this region of charge on this entire molecule because it is totally polar due to the fact that I have a carbon-oxygen polar bond, right? And so now, rather than having these regions of electron cloud polarizability where they're like negative on a side of the electron cloud, now I have the entire molecule has a side that's negative and a side that's positive. If these guys are sort of like moving around in space and like tumbling over each other, now I have sort of a partial positive side over here that can engage in attractive forces with the partially negative side of this molecule. And that dipole is permanent. It's not going away. All right, so that is what we call a dipole-dipole force, where I have like a positive side on this end of one and a negative side on the other one. And when they're all tumbling around each other, they're going to engage in intermolecular forces. And those are permanent. So those aren't going away. Those are stronger than what we would call a temporary dipole. That's a London force. But in addition to that permanent dipole, I also have the opportunity for these guys to engage in, you know, London dispersion forces also, because they have electrons that are moving around and can be polarized. So everything has those London forces, and only polar molecules have dipole-dipole forces. Now, the bigger the shift in electron density towards one atom, the more electronegative this side becomes, and the more sort of electropositive the other side becomes. So the bigger the dipole, the stronger that attractive force is. So remember, the more positive something is and the more negative something is, the stronger that electrostatic attraction is. So the bigger the dipole on that polar molecule, or what we call the dipole moment, which you can actually find, like it's a number, the stronger the dipole force will be. Now let's say I have what we call the dipole force on steroids, where I have bonds that are so extremely polar that they are, this just bugged me, sorry. I did that out of order. And F, where these are so polar that we're giving them their own name. We call them hydrogen bonds. All right. And this is, let's see, the difference between these H and F, my table. Hydrogen is 2.1 and nitrogen is 3.0. So this is 0.9 all the way up. I believe this is 1.9. All right. Now, the reason why this is so important is because this guy is so small and these guys are super, super small. So they're like basically like a bare proton and like some other super electronegative atom. Now, what makes these super special, it's not like I look in the molecule and I see a hydrogen and I see a nitrogen. I'm like, oh, awesome hydrogen bond. They have to be bonded to each other in order for that to count because you need that really, really polar bond. So what that is talking about is like, well, let's go back up here. It's like saying I have this polar region on the molecule that is super, super polar. Well, now I have like an extra megapolar region that isn't going away, and we call that a hydrogen bond. So like anytime we have, if we have like H3C, COH, anytime I have something like that, all of a sudden I just have this region of charge that is so electronegative and so electropositive on the other end that I have this really, really strong, like a really strong intermolecular force. Now let's say I have a molecule that has all of these things, right? And I have this. It's a carboxylic acid. So bam, I have a dipole because that's a polar bond, and I have a hydrogen bond. And whatever's else over here is engaging in London dispersion forces. Everything is. So if I were to give the intermolecular forces for this substance, I would say LDS because it has electrons, check. It has a dipole, so dipole, dipole, and it has a hydrogen bond. Now, which one predominates? Like, which one is the most significant in determining the overall strength of these forces? It's going to be the strongest one, which is the hydrogen bond. And we signify that typically by putting a star next to it. Okay, hopefully that makes a little bit more sense and you understand a little bit better how you can have more than one type of intermolecular force in molecules.